The Milky Way feels impossibly large. It contains hundreds of billions of stars, stretches across more than 100,000 light years, and has been our cosmic home for as long as humanity has looked up at the night sky. For a long time, it was easy to believe that our galaxy was something special. After all, it was the only one we truly knew. Then astronomers took a closer look beyond it. Just 2.5 million light years away lies another spiral galaxy. At first glance, it appears as nothing more than a faint patch of light in the night sky. You can even see it without a telescope under dark skies. It looks quiet, small, almost insignificant. But appearances can be incredibly misleading. That faint glow is an entire galaxy, a city of roughly 1 trillion stars, a system so vast that even light, the fastest thing in the universe, needs about 220,000 years to travel from one side to the other. And despite the unimaginable distance between us, that galaxy is slowly getting closer. Every second, Andromeda moves a little nearer to the Milky Way. Not because the universe is shrinking, not because gravity has failed, but because these two giant galaxies have been falling toward each other for billions of years. One day, they won't simply pass by. They'll merge. The night sky will change forever. But before we can understand that future, we first need to understand what Andromeda really is. Not just another galaxy, but one that completely changes our sense of scale. Because once you truly understand the size of Andromeda, the universe never feels the same again. Long before anyone knew what galaxies actually were, Andromeda was already part of the human story. Ancient sky watchers noticed a faint, misty patch of light among the stars. Unlike the planets, it never wandered across the sky. Unlike a comet, it never developed a tail. It simply remained there, year after year, century after century. For thousands of years, nobody knew what it was. Some believed it was a cloud of glowing gas. Others assumed it was a distant nebula inside the Milky Way. That idea seemed reasonable. After all, at the beginning of the 20th century, many astronomers believed the Milky Way was the entire universe. If every visible star belonged to one enormous galaxy, then mysterious objects like Andromeda had to belong to it as well. But one question refused to disappear. Why did some of these so-called nebulae look different? Why did they show spiral structures? Why did they appear far too large and too organized to be simple clouds of gas? Those questions led to one of the most important scientific debates in modern astronomy. It became known as the Great Debate. In 1920, astronomers Harlow Shapley and Heber Curtis argued over the true nature of spiral nebulae. Shapley believed the Milky Way contained everything. Curtis believed these spirals were separate galaxies, entire island universes scattered throughout space. At the time, neither side had enough evidence to prove their case. The answer arrived just a few years later. In 1923, Edwin Hubble observed individual variable stars inside Andromeda using the Hooker telescope at Mount Wilson Observatory. These stars, known as Cepheid variables, behave like cosmic measuring tapes. Their brightness changes in a predictable way, allowing astronomers to calculate their true distance. Hubble's measurements revealed something astonishing. Those stars weren't thousands of light years away. They were more than 1 million light years distant, far beyond the edge of the Milky Way as it was understood at the time. There was only one possible conclusion. Andromeda wasn't part of our galaxy. It was another galaxy entirely. That single discovery instantly expanded the known universe. Humanity went from living inside what seemed like the only galaxy to realizing the universe was filled with countless others. It's difficult to overstate how profound that moment was. Astronomy didn't simply gain a new object to study. It gained an entirely new universe. Today, we know Andromeda as Messier 31, or simply M31. It is the largest galaxy in the local group, a small collection of more than 50 galaxies bound together by gravity. Most of those galaxies are relatively small dwarf galaxies. Only a few dominate the group: the Milky Way, the Triangulum Galaxy, and above them all, Andromeda. Located about 2.5 million light years from Earth, it's the closest large spiral galaxy to our own. That distance sounds enormous, and by any everyday standard, it certainly is. Yet on the scale of the observable universe, Andromeda is practically our next-door neighbor. Light leaving Andromeda tonight won't arrive at Earth for another 2.5 million years. In other words, every time we look at Andromeda, we're seeing it as it existed long before modern humans appeared. The galaxy we observe today is a snapshot from Earth's distant past. Astronomy has a unique way of turning distance into time. The farther we look, the further back in history we see. One of the most surprising facts about Andromeda is that you don't need expensive equipment to find it. Under dark skies, away from city lights, it's visible with the naked eye. That makes it the most distant object most people will ever see without a telescope. It's an extraordinary thought. A faint smudge no larger than your fingertip held at arm's length contains roughly 1 trillion stars. Many of those stars almost certainly host planets of their own. Some may have moons. Some may possess atmospheres. Some may even resemble worlds we're only beginning to imagine. From Earth, however, they blend together into a soft glow barely visible against the darkness. Distance has a remarkable way of hiding complexity. At first glance, Andromeda looks similar to the Milky Way. Both are spiral galaxies. Both contain spiral arms filled with gas, dust, and young stars. Both have older stellar populations concentrated toward the center. Both are surrounded by halos dominated by dark matter. Yet Andromeda isn't simply another version of our galaxy. It's larger. Its visible disk stretches approximately 220,000 light-years across, making it significantly wider than the Milky Way. For many years, astronomers also believed it contained substantially more mass. Recent measurements suggest the total masses of the two galaxies may actually be closer than once thought, largely because dark matter dominates both systems. Even so, Andromeda remains more expansive in its visible structure and likely contains around 1 trillion stars, compared with the Milky Way's estimated 100 to 400 billion. That's one reason astronomers often describe Andromeda as our giant neighbor. Not because every measurement is dramatically larger, but because nearly every part operates on a grander scale. Its spiral arms aren't just beautiful patterns. They're enormous stellar nurseries. Clouds of hydrogen collapse under gravity. New stars ignite. Massive blue stars flood their surroundings with intense ultraviolet light. Supernova explosions enrich the galaxy with heavier elements. Over millions of years, those elements become part of new stars, new planets, and potentially new planetary systems. Galaxies aren't static collections of stars. They're ecosystems. Matter is constantly recycled. Stars are born. Stars die. New generations emerge from the remains of the old. Andromeda has been repeating that process for billions of years. Long before Earth existed, its galaxy was already building new worlds. At the very center lies another reminder of nature's extremes. Like the Milky Way, Andromeda hosts a supermassive black hole, known as M31*. It's estimated to contain well over 100 million times the mass of the Sun, making it significantly more massive than Sagittarius A*, the black hole at the center of our own galaxy. Despite its enormous mass, occupies only a tiny fraction of the galaxy's total size. It's a powerful reminder that galaxies aren't defined by a single object. Their true scale comes from the countless stars, nebulae, star clusters, dark matter, and invisible gravitational structures working together over billions of years. And once astronomers began measuring those structures, they realized something even more astonishing. The bright spiral galaxy we see in photographs is only a small part of the real Andromeda. The vast majority of its true size remains completely invisible, and that's where our journey continues. When we look at photographs of Andromeda, it's easy to assume we're seeing the entire galaxy, a bright central bulge, graceful spiral arms, dark lanes of dust stretching across a glowing disk. It feels complete. But those stunning images tell only part of the story. The visible galaxy is merely the brightest layer of something far larger. Beyond the spiral arms lies an enormous halo of stars so faint that it remained almost invisible for decades. Even farther out is an even larger halo made almost entirely of dark matter. Together, these hidden structures extend Andromeda far beyond what our eyes, or even most telescopes, can easily detect. In other words, The galaxy is much bigger than the picture suggests. The visible disk measures roughly 220,000 light-years across. That's already an astonishing distance. If a beam of light left one edge of the galaxy today, it would spend approximately 220,000 years crossing the disk before reaching the opposite side. To put that into perspective, modern humans have existed for only a fraction of that time. Civilizations have risen and fallen. Languages have appeared and disappeared. Entire chapters of human history would pass before that single beam of light completed its journey. And that's only the bright part of the galaxy. The invisible halo stretches much farther. Some estimates suggest it extends well beyond 1 million light-years, overlapping with the outer halo of the Milky Way long before the two galaxies themselves collide. That means the first stage of their interaction has already begun. Not through stars, not through planets, but through the vast gravitational structures surrounding them. Gravity is the true architect of every galaxy. Stars may provide the light, but gravity determines the shape. Without it, galaxies wouldn't exist. Every star inside Andromeda is constantly orbiting the galaxy center. Some complete an orbit in a few 100 million years. Others require much longer. Even our own sun needs about 230 million years to circle the center of the Milky Way just once. Galaxies don't rotate like solid objects. The inner regions move at different speeds than the outer regions. That difference creates the beautiful spiral patterns we observe across the universe. Yet when astronomers measured Andromeda's rotation, they discovered something unexpected. The outer stars were moving far faster than visible matter alone could explain. According to Newton's laws, those stars should have drifted away long ago. Instead, they remained in stable orbits. The missing ingredient was something invisible: dark matter. Dark matter doesn't emit light. It doesn't reflect light. It doesn't absorb light. In fact, no telescope has ever seen it directly. Astronomers know it exists because of gravity. It's the invisible framework holding galaxies together. In Andromeda, dark matter outweighs all the visible stars, gas, and dust combined. Without it, the galaxy we admire today would never have formed. This realization completely changed modern astronomy. The bright spiral filling magazine covers and telescope images isn't the galaxy's largest component. It's simply the part we can see. The real Andromeda is dominated by something completely invisible. Stars themselves tell another story about the galaxy's immense scale. Current estimates suggest Andromeda contains around 1 trillion stars. That's an almost impossible number to visualize. Even if someone could count one star every second without ever stopping to sleep, eat, or rest, reaching 1 trillion would take more than 31,000 years. And that's only the stars. Each one may host its own planetary system. The Milky Way has already shown us that planets are common. There's every reason to believe Andromeda is no different. Some stars may have one planet. Others may have many. Some planets could be frozen. Others scorched by intense radiation. A few may orbit within regions where liquid water is possible. The numbers quickly become overwhelming. If only 1% of Andromeda's stars hosted Earth-sized planets, that would still represent billions of potentially rocky worlds. The galaxy isn't simply larger than ours. It contains billions of opportunities for entirely different planetary systems to exist. Yet stars are not spread evenly throughout Andromeda. The galaxy is structured. Its central bulge is densely packed with older stars that formed billions of years ago. Moving outward, the spiral arms become richer in gas and dust. These regions serve as stellar nurseries where new generations of stars continue to form. Farther still lies the halo. Unlike the orderly spiral disk, the halo is a sparse population of ancient stars and globular clusters surrounding the galaxy in every direction. Some of those globular clusters are among the oldest structures in the local group. They formed when the universe itself was still young. Studying them allows astronomers to reconstruct Andromeda's history, almost like reading fossil records preserved across billions of years. That history wasn't peaceful. Galaxies grow by merging. Throughout its lifetime, Andromeda has absorbed numerous smaller galaxies. Each merger left behind faint streams of stars stretching across the halo. For years, these stellar streams were invisible. Modern surveys eventually revealed them as enormous arcs wrapping around the galaxy. They're the remains of ancient galaxies pulled apart by gravity. Each stream is evidence of another chapter in Andromeda's past. In many ways, the galaxy we see today is a result of countless smaller galaxies becoming one. Growth in the universe rarely happens quietly. It happens through gravity. As astronomers map these structures, they notice something remarkable. Andromeda isn't alone. More than 30 known dwarf galaxies orbit around it. Some are compact collections of ancient stars. Others still contain gas capable of forming new generations of suns. Together, they create a miniature galactic ecosystem. The Milky Way has its own family of satellite galaxies. So does Andromeda. Both giants dominate their local neighborhoods, shaping the motion of everything nearby through gravity alone. On even larger scales, these galaxies belong to the local group, a gravitationally bound collection spanning roughly 10 million light-years. Within that enormous volume of space, the Milky Way and Andromeda account for most of the visible mass. They're the two giants of our cosmic neighborhood. Everything else moves under their gravitational influence. Perhaps the most surprising lesson isn't that Andromeda is larger than the Milky Way. It's that our entire galaxy is small compared with the universe beyond. The observable universe contains hundreds of billions of galaxies. Some are tiny dwarf galaxies containing only a few million stars. Others are giant elliptical galaxies containing trillions. Andromeda is enormous by the standards of our local neighborhood. But even it is only one chapter in a much larger cosmic story. Understanding its scale doesn't make the universe feel smaller. It does the opposite. It reminds us that every galaxy we discover is part of an even greater structure stretching across billions of light years. The deeper we look into space, the more our sense of scale continues to expand. And yet, despite all that distance, despite the trillions of stars, despite millions of light years separating us, Andromeda is heading toward us. Every second, gravity pulls these two giant galaxies a little closer together. The collision won't happen tomorrow or next century, but it's already inevitable. And when it finally begins, it will become one of the greatest events in the future history of our cosmic neighborhood. That's the story we'll explore next. For most of human history, the night sky appeared permanent. The constellations never seemed to change. The Milky Way stretched across the heavens exactly as our ancestors had seen it. It gave the impression that the universe was still, timeless, unchanging. But astronomy has revealed a very different reality. Nothing in the universe remains the same forever. Stars are born, stars die, planets form, galaxies evolve. Even the largest structures in the cosmos are constantly moving. And among all the future events astronomers have predicted, few are as extraordinary as what awaits the Milky Way and Andromeda. For billions of years, gravity has been quietly pulling these two galaxies toward one another. Today, Andromeda is approaching the Milky Way at roughly 110 kilometers per second. That may sound incredibly fast, yet across a distance of 2.5 million light years, even that speed requires billions of years to close the gap. Nothing about this journey is sudden. Galaxies don't collide the way cars do. They perform a gravitational dance that unfolds over immense stretches of time. Current models suggest the first close encounter will occur in about 4.5 billion years. By then, the Earth itself may already be facing an entirely different challenge. Around that same period, the Sun will begin exhausting the hydrogen fuel in its core. It will gradually expand into a red giant, transforming the inner solar system long before the galaxies complete their merger. The future of Earth and the future of the Milky Way are unfolding on remarkably similar timescales. The word collision often creates the wrong image. People picture stars crashing into one another, entire solar systems being destroyed, explosions filling the galaxy. The reality is far more surprising. Galaxies are mostly empty space. Although Andromeda contained around 1 trillion stars, the distances separating those stars are so enormous that direct stellar collisions are extremely unlikely. If two galaxies the size of the Milky Way were compressed until each star became a grain of sand, the grains would still be separated by kilometers. The galaxies themselves overlap. The stars almost never do. Instead of violent impacts, Gravity slowly reshapes billions of individual orbits. Stars drift into new regions. Some move closer to the galactic center. Others are flung far into intergalactic space. The galaxies don't shatter. They reorganize. That process begins long before the visible disks actually touch. Remember the enormous dark matter halos surrounding both galaxies. Those invisible structures extend far beyond the bright spiral arms. In fact, astronomers believe the halos may begin interacting hundreds of millions of years before the first visible signs of the merger appear. Gravity doesn't wait for galaxies to make contact. Its influence reaches far beyond what telescopes can see. The collision begins in darkness, long before it becomes visible in light. As the galaxies pass through one another, gravity compresses vast clouds of hydrogen gas. Those clouds collapse. New stars ignite. Regions that were once relatively quiet become intense stellar nurseries. Astronomers have observed this process throughout the universe. Whenever large spiral galaxies merge, star formation often increases dramatically. Entire clusters of young, brilliant blue stars can appear over comparatively short cosmic timescales. Ironically, destruction creates opportunity. The same gravitational forces that disrupt existing structures also trigger the birth of countless new suns. It's one of the recurring themes of the universe. Creation and destruction are rarely separate events. More often, they happen together. The solar system will also respond to these changing gravitational forces. Current simulations suggest our sun is unlikely to collide with another star. The distances remain simply too vast. However, its orbit around the galactic center may change significantly. The solar system could migrate farther from a galaxy's core. It could move into an entirely different region of the newly forming galaxy. Or, although considered less likely, it could even be ejected into the outer halo. No matter which outcome occurs, one thing is almost certain. The night sky would become unrecognizable. For millions of years, Andromeda would grow larger and brighter. Its spiral arms would stretch across the heavens. Eventually, both galaxies would fill enormous portions of the sky as gravity twisted them into spectacular arcs of stars and glowing clouds of gas. If intelligent observers still existed within the solar system, they would witness the greatest astronomical display in Earth's history. Not a meteor shower, not a solar eclipse, but the slow transformation of two galaxies becoming one. That new galaxy already has an unofficial name, Milkomeda. Some astronomers also refer to it as Milkdromeda. Whatever the final name becomes, its appearance will likely be very different from either galaxy today. The graceful spiral arms of the Milky Way and Andromeda probably won't survive. After billions of years of gravitational interactions, computer simulations suggest the merged galaxy will resemble a giant elliptical galaxy. Its stars will orbit in more random directions. The elegant spiral pattern that has defined both galaxies for billions of years will gradually disappear. Galaxies evolve just as stars do. Even structures spanning hundreds of thousands of light years have life cycles. This isn't a rare event. Across the observable universe, astronomers have photographed galaxies in every stage of the merging process. Some are just beginning to interact. Others display enormous tidal tails stretching hundreds of thousands of light years into space. Some have already become single, larger galaxies. By studying those distant mergers, astronomers are effectively looking into the future of the Milky Way. The universe has already performed this experiment countless times. We're simply watching another example unfold. Perhaps the most remarkable part of Andromeda's story isn't its size, nor its trillion stars, nor even the future collision with our own galaxy. It's what the galaxy represents. Just 100 years ago, humanity wasn't even certain Andromeda was another galaxy. Today, we can estimate its mass, measure the motion of its stars, map its dark matter, study its black hole, analyze the chemistry of its star-forming regions, and predict how it will evolve billions of years into the future. That's an extraordinary leap in understanding, not because Andromeda became easier to study, but because humanity learned how to ask better questions. Every generation inherits a larger universe than the one before it. And perhaps that's the greatest lesson hidden within our giant neighbor. The universe isn't built to remain the same. Everything changes. Stars evolve. Galaxies merge. New worlds form from the remnants of old ones. The cosmos isn't a collection of frozen objects suspended in space. It's a living history of constant transformation. Andromeda reminds us that even the largest structures we can see are only moments in a story still unfolding. One day, it will no longer be our neighboring galaxy. It will become part of our own, not through violence, not through catastrophe, but through the quiet, patient force that has shaped the universe from the very beginning. Gravity. Every galaxy has a history. Every galaxy has a future. And every point of light in the night sky is part of a universe that's still evolving. When we look toward Andromeda, we're not simply looking at another galaxy. We're looking at our future. We're looking at one chapter in a much larger cosmic story. A story written across billions of years and billions of light years. The true scale of Andromeda isn't measured only by its size. It's measured by the perspective it gives us. Because once you understand how vast one galaxy can be, you begin to understand just how extraordinary the universe truly is.